Perfect. Okay, yeah, so over the semester, Khushi and I have basically researched the regional class research vessel. It was super duper interesting because obviously the oceans are changing a lot nowadays and they always are. And so we were able to research these research vessels that basically explore the ocean, food chains, how climate change is affecting it, what the pollution is like throughout this entire semester. And so just a little bit about both of us. My name is Mia Patel. I go to the University of Notre Dame. Last semester, I was actually a business or a finance student, but a finance major, but I switched to computer science. And throughout this internship, I've learned a lot about just technology and the technology space in general, outside of just, coding in C every single day. And, creating these projects, I got to basically apply a lot of those things to this internship. And so it's made me a lot more excited about computer science as a whole.
And like me, I really enjoyed this internship, learning about techniques and about the CI conference program.
I'll begin again. So there are 3 vessels that are being constructed. And so the first operations were supposed to take place in March 2022, and the other 2 will be in 6-month increments ending in February 2023. And so when we talk about regional class research vessels, we're basically referring to these 3 ships that act as floating laboratories. And they're supposed to be at different positions at sea or different locations. So one is supposed to be near the coastal US, that'll be used by oceanographers. Another is supposed to be primarily in the Pacific Ocean, one in the Atlantic, and then the other near the Gulf of Mexico or in the Caribbean Sea. So the use of these are to be general purpose research ships that will allow for oceanography research. And so this is to understand the ocean's resources, processes, and marine life processes. And there's a series of questions on the right-hand side of the screen. And these are questions just taken from the NSF website about scientific priorities that they want to find. They want to gain knowledge about through regional class research vessels. And so some of these are like, how has the ocean processes changed and contributed to today's climate? And then what processes can control the formation and evolution of ocean basins?
And then I'm just going to talk a little bit more about just the key features of the research vessels. First of all, there's gear deployment, which basically allows for just nets and equipment to be deployed from the ocean. This also includes like robotic arms that maybe if the ship wants to like pick up some like rocks or look at other artifacts in the oceans, it's able to do that. It's able to catch any marine life that it wants to. One thing that kind of surprised me is I never thought about like how, like a lot, like the ocean is pretty treacherous and a lot of these research vessels are not able to move because they need to collect data. And so this research vessel specifically has dynamic positioning, which basically allows it to stay in place or move in a straight path along the ocean while also exploring like deep parts of the ocean without moving, because it's incredibly hard to do that if the ocean is basically moving the vessel constantly. And it does not use an anchor. Instead, it uses basically 2 propellers that kind of act as wings in order to keep it in place. And Khushi's going to expand on this more, but also has data presence, which basically allows data to be real time sent to the laboratories on land. So there's planning tools, situational awareness, streamlined workflow, outreach pipeline, and maintenance and management, just to make sure that the data is properly sent and analyzed from the ship, even though the data is not actually being collected on land. There's also a U-tube anti-roll tank, which basically is used to minimize rolling, which plays into just allowing the ship to stay in one spot instead of, having it move around and making it harder to collect data. There's a bulbous bow, which basically allows it to go through treacherous water. A lot of these ships are deep in the ocean. They're not near land at all. And so they need to be able to move through water that's not as smooth as something that you'd see closer to the coast. And lastly, a center board, which basically is kind of a laboratory and also just allows the ship or allows to collect data about the currents, capture images, and identify organisms on ship and send it back to the land laboratories.
Okay, so what are the capabilities of the ship? So the design of the ship allows it to be capable of several different things. So there are a number of tasks that the ship should be able to do. So for example, the ship should be able to sample and collect data at almost any type of sea level. So this includes surface, midwater, and seafloor parameters. It will be done, and the data will be collected and then will be analyzed through scientific laboratories. Another capability is the launch and recovery of scientific packages. So scientific packages refers to any sort of tool or device used at sea that could help understand the ocean better. This could be scientific equipment, and this could also include underwater robots. And it's also supposed to have the capability of mapping the seafloor, which helps get a large scale view of the entire seafloor in the ocean. And it's also supposed to be responsible for launch and recovery of several different types of equipment and systems. So this includes scientific packages, equipment, and underwater vehicles, which are tools and devices that would be used to collect data at sea. And then we wanted to highlight, like what Mia was saying, like an aspect of regional class research vessels, which is data presence. And basically data presence is, it has a lot to do with data collection. And data presence is a newly developed technology that allows for research vessels to have virtual participation and have virtual research to be facilitated in real time. And this is done through strong satellites that are located in the ship. And so this basically allows scientists ever to be involved in the seagoing operations, because the boat can only hold so many people. People on the shore are allowed to help contribute and analyze the data as well. Data is going to be able to be integrated by the sensors of the ocean, and it allows for data collection and data visualization to take place. And so the hope is for shoreside participation to take place while researchers are at sea, and also to encourage education and community outreach. So data presence allows for the data being collected at sea to be backed up, and feedback can be almost instantaneous. And so a public portal would be allowed to, this allows for educators and outreach who have hopes of advancing ocean and atmospheric literacy to take part in the data collection that's being taken place.
And just a little bit more about the future of RCRV. Of course, we all know that the oceans are changing due to climate change. A lot of marine life is being affected. Food web chains are changing constantly. There's a lot of pollution. And so RCRV these research vessels are becoming like a lot more popular, and they're being built. And so there's a new one that's going to be deployed basically in 2023 that will be exploring the Atlantic Ocean, which has had a lot of issues due to climate change and pollution.
And that's the end of our presentation.
I said, oh, great. Any questions for these two?
So I have a question. What was the most surprising thing that you found out about research vessels? You know, something that you thought, wow, you know, I would never think of that.
For me, you can go first.
Basically, like when I think of ships, I usually think of like cruise ships. I've never really thought that there were research vessels out there. Obviously, I knew they existed. But one thing that surprised me is and kind of one challenge I saw that I was very surprised they fixed is like just staying still in an ocean environment, like such as like the middle of the Atlantic Ocean, where like everything it's pretty treacherous. I know they already have like propellers that fix that issue, but I would just wonder like how there has to be only a couple days of the year where they can really collect like effective data. So I was just wondering like when that was and like how they basically go around that whole ordeal.
Okay.
For me, I would say probably the concept of data presence, because it's very interesting just to learn about how data can be live streamed from the sea, because you don't really expect that to happen. And I like how they are taking an initiative to try to teach it to students as well. So that's probably the most interesting thing that I've learned.
Mm. Yeah, I agree. Both these topics are very interesting, and in the summertime, we might be exploring the topics of data presence, and we're looking right now at some of the potential applications that we can help out with in that area. So, it's great to know that you guys are interested in that.
Okay, so we're going to move on to Nona and Ryan. Thank you, Khushi and Mia.
And if I can make one more comment, so clearly the data presence is very serious focus, but I think the keeping the ship in position, I would imagine, requires a lot of computer science and IT to really triangulate the position appropriately and guide the propellers to keep the ship in place. So there's a lot of applied CS there. Sorry.
Hi, this is Ryan, and I'm working with Nona. And yeah, shall we begin?
Yes.
Okay, so me and Nona, we are doing research on NCAR. And so first, a little bit about both of us. So my name is Ryan. I'm a student intern in this program. I go to University of Southern California. I'm currently a junior studying computer science, minor in game programming. A little bit past experience about me was I was former content provider of USC's algorithm class, CSI 270, and I was also a former iOS development intern at Alibaba. And I'm currently exploring topics about major facilities, game engine programming, as well as AI. And now about Nona.
Hi, my name is Nona. I also go to USC. I'm a freshman studying computer science with a focus on software engineering or cloud computing. I'm currently working towards my Amazon Web Services Cloud Practitioner certificate, as well as researching digital healthcare application in wars and refugee camps, as well as researching about MFs, which is what we will be presenting today. So a little bit about NCAR. There are 5 focuses about that the NCAR has: weather, water, climate, air quality, and sun plus space weather, which is kind of connected. And we decided to pick, each one of us decided to pick one topic out of all of these and just one specific instrument that we could research, because there were so many. We researched a lot throughout the semester, but we decided to pick one of our favorites to present to you guys today. So I decided to pick COSMO, which is the coronal solar magnetism observatory. It has 2 instruments. We will be going over all. It has 3 instruments. We'll be going over all 3, but our main focus is the LC on the top left. So solar activity, including solar eruptions, known as coronal mass ejections, otherwise known as CMEs. They get its energy from the coronal magnetic field, and this activity affects space weather and also damages satellites, and also affects communication and creates hazard for astronauts in space. COSMO tracks this energy built up in the sun's magnetic field and changes in the plasma, and this helps us provide information to communication places or just astronauts so they could avoid the hazards. And COSMO is comprised of 3 instruments to capture these observations. So a little bit about the data capture. The top left one we see, the LC, otherwise known as the large coronagraph, is the central instrument of COSMO. So most of the data we get from the LC. It observes light produced by multiple coronal emission lines by using NIRS, which is the red thing we see at the very top. The CHROMAG, otherwise known as a chromospheric and prominence magnetometer, measures the magnetic field in the plasma conditions below the corona and in the solar chromosphere. And the K coronagraph, otherwise known as the K core, observes low corona in the brown light. So in other words, the LC observes the light produced by the coronal emissions. The CHROMAG measures the magnetic field and the plasma under the magnetic field. And the K core observes, otherwise known as the white light, I guess we could say. So if you could go to the next slide. So this is a chart that we found during our research of the initial and central processing summarized. So to go over it, as you can see, we have different levels. And to start with level 0, this is the processing, and it's defined as the steps to transform raw data into level 0 data. And level 0 processing steps are performed at a very low level in real time. So it takes a while because it's saved before it's saved to the disk. These steps include correction for bit errors and things like that, and data taken during over some time selectable time interval at the same wavelength and polarization state will be averaged over a number of modulation cycles. Next, we see level 1 processing, which refers to the reduction steps required to create fully calibrated level 1 data from the level 0 data that we previously spoke about. And level 1 processing includes bias and gain calibration, and also polarization calibration. And then the next, we have the level 2 processing, which converts level 1 data into level 2 science data products. These include Doppler maps, LOS magnetic field strength, POS field direction maps, and things like that that the public can use. Also temperature maps, which could also help communication facilities. And the next slide, we have storage, curation, and archiving, plus the data access and how it's available to the public. So this figure kind of shows the figure that we talked about earlier, but it's more generalized and shows the storage and how everything works. So this is the data flow in the Cosmo Observatory with the processing steps included from before. The top half of the figure shows the operations at the observatory, and the bottom half of the figure shows the operations at the data center. The dark blue box at the top left that we can see is the ICS instrument control system for the LC that I talked about earlier. It provides instrument control and level 0 processing. And then the green box in the figure that we see is the Cosmo data handling system, otherwise known as the DHS computer, which acts as the data handling storage component between data level 0 data that we get from real time. And it's processed into long-term storage at the Cosmo data center. The DCS is where all the Cosmo instruments provides display, and the light blue box that we see represents the Cosmo data center where level 1 and level 2 processing takes place, and where the data will be made available to the public community and through the Cosmo webpage that we talked about earlier with Doppler maps, LOS magnetic field strength, and temperature maps.
Okay, so NCAR's other goal is to understand the behavior of the atmosphere and the related Earth system. And then NCAR has this community Earth system model, aka CESM, to support research in this area. And first, I want to talk about the history of CESM. The original model was not called CESM. It was called Community Climate Model, aka CCM. It was established in 1983. It has two major components, the atmosphere component and the land surface component. And a little bit later, in 1994, NCAR added two more components about the global ocean and the CS. And they changed the name into climate system model, which is called CSM, because now this model is more comprehensive and it simulates the land, ocean, atmosphere interactions. And later on, in order to recognize the community of users and sponsors, NCAR changed the name of CSM into CCSM. It was done in 1996. The full name is called Community Climate System Model. And currently, and nowadays, the model changed its name again. It's called Community Earth System Model, CESM. And it has many specialized components. It is a comprehensive coupled climate system. And by coupled, the term coupled means the component depends on each other and they form a comprehensive and complicated system for better and more accurate simulation of the Earth. And here is a GitHub portal of CESM. When we refer to CESM, we usually refer to the entire CESM system, as well as each component that it comprises. And as you can see here, that inside this portal, we have CAM, Community Atmosphere Model, which is a part of the entire system, and as well as the CESM, which is like the very initial Git repo of CESM. But when we talk about CESM, we refer to the entire system. And we also have this CTSM community. It's basically about the land surface. It also includes the community land model of CESM. And so again, CESM is a comprehensive system that contains lots of subsystems and components. It has specialized models to simulate the atmosphere, the ocean, and the land. And within those models, there are components about tropospheric chemistry, about land ice, sea ice, river waves, and so on. And moreover, CESM has been and is continuously incorporating new submodels into its system, and it is evolving into an even more comprehensive and more accurate simulation of the real world. And next, I want to talk about the data life cycle related to CESM. So in general, a complete data life cycle contains 5 phases: data capture, initial processing, central processing, storage, curation, archiving, data access, dissemination, and visualization. And specifically about CESM, NCAR has a bunch of instruments for data capture. And NCAR has a bunch of instruments and facilities for data capturing, which includes research aircrafts and several specialized observing facilities. And for data processing, NCAR has the supercomputer Cheyenne, and also the Casper cluster, which is a heterogeneous system specialized for data analysis and visualization. It features large memory, multi-GPU nodes, and high throughput computing nodes. And then I want to talk about data archive and visualization. So all of this data processing instruments, they provide computational power where the CESM model can be run and output valuable results for the scientists. And to store and visualize the results, NCAR has this GLADE data storage system, and it also shares data with other MFs because it's called community. It has a community, the word community in the name of the system. It already share data with NASA or WCRP. The output of the model is accessible via NCAR's archive system. And here are some screenshots I took from NCAR's data archive system. Everything is well organized, and the metadata, metadata here clearly categorized them. And you can see there are pictures and yeah. And if I take a closer look, if I click on this metadata here, you can see that it contains metadata about years of record, formats, timestamp, and a lot of other things. So everything is organized, and it has all this makes it easier for user to search and access them. Yeah, and that basically concludes our presentation today. Thank you.
Thanks. Any questions for Ryan and Nona? We've got time for, we've got 3 minutes for questions.
I just want to comment that, like Arnie Brand said, I'm learning a lot of stuff from you guys. So this is great. I love it that you mapped it to the data lifecycle. So thank you.
Yeah.
Time for another one if anyone has one.
Yeah. The solar observing the processing steps as it cooks down and produces more detailed, less detailed, more abstract. Is that what they use for the alerts, like when they page satellite operators and tell them you got a bad one coming?
I don't think that's the only thing that they use, but it definitely takes part in what they use, because NCAR has many different instruments that we've covered through the year.
Okay, thanks.
Good question, Eric. All right, why don't we move on then to Edward and Christy, who are going to talk to us about National Solar Observatory? National doesn't sound right to me all of a sudden, but NSO. And by the way, everyone, Chris Romsos from RCRV joined.
Hi, Chris.
Hello, sorry I'm late. Okay, so today, Christy and I are going to be talking a little bit about the National Solar Observatory. Like this was the MF that we were assigned to research.
Hi, everyone. An introduction about me is that my name is Christy. I'm a student intern here at CI Compass. I'm a freshman at USC and a major in computer science and business administration. If you ever want to contact me, that's my email.
I'm also an intern here at CI Compass. I'm a sophomore here at USC. I'm a computer science major. And that's my email too.
Okay, so what is the NSO? Their mission is to advance knowledge of the sun as an astronomical object and as an external influence. They have 3 projects that we'll focus on today, and I'll be talking about GONG and DKIST. So GONG is the Global Oscillations Network Group, and they conduct a detailed study of the solar internal structure and dynamics using helioseismology. And DKIST is another telescope that measures the magnetic structures at the solar surface and outer atmosphere.
And SOLAS, which stands for Synoptic Optical Long-Term Investigation of the Sun, it provides unique observations of the sun like on a continuing basis for several decades in order to understand the solar life cycle and sudden energy releases in the solar atmosphere and solar irradiance changes in the relationship to our planet as a whole.
So a bit of background about DKIST is that it is located in Maui, which is 10,000 feet in elevation, and it's surrounded by ocean. And the reason it's in this location because the dark blue skies are needed to observe the faint corona of the sun. And the high elevation also lets there be low air turbulence in the atmosphere. And so there are 5 main parts to DKIST. There's the visible spectral polarimeter, which observes the magnetic field of the sun, the visible broadband imager that takes high spatial resolution images of the solar surface and a low atmosphere, the visible tunable filter, which explores the evolution in the morphology of the layers of the solar atmosphere. And there's also the diffraction limited near infrared spectral polarimeter that measures solar magnetic fields at high spatial resolution and polarimetric accuracy. And there's a cryogenic near infrared spectropolarimeter that studies the solar coronal magnetic field over a large field of view at near and thermal infrared wavelengths. There's also FIDO, which basically operates the entire process. They use like optics and like mirrors to like guide the light into the lenses and the polarimeters. And how the data is transferred in DKIST. The main producers of the data is from the visible broadband imager and the visible tunable filter, which can be up to 960 megabytes per camera. And from the site to the data center at University of Colorado Boulder, there are data transfer and test nightly, and they fluctuate between 80 megabits to 150 megabytes per second. And NSO's goal is they want 10 gigabytes per second bandwidth physically available. And when it's fully operational, they estimate that it will have an average of 8 terabytes of data per day and 6 petabytes of data per year. And how it works is that they have 5 dedicated data pipelines for each instrument. So, and the pipelines can also be shared among several instruments as well.
Now to talk a little bit about SOLAS. SOLAS consists of 3 different instruments mounted on a common observing platform. These 3 instruments being the vector spectromagnetograph, integrated sunlight spectrometer, and the full disk control. And it's mainly a synoptic facility for solar observations over a long time, as mentioned before, and provides unique observations of the sun. And I believe it was installed and hit peak in 2003 and moved to Tucson in 2013. And it's currently at Big Bear Observatory, where a more permanent site for it is being built. And now to talk a bit about the instruments, which are all used to study magnetic and non-magnetic solar activity with high spectral moderate spatial resolution. And firstly, the vector spectromagnetograph provides full disk vector maps of the solar magnetic field, both in the photosphere and in the chromosphere on a daily basis. And the data products mainly include different magnetograms, such as seen here, the photospheric full disk vector magnetogram, and so on. And hardware-wise, it consists of a Ritchie-Chrétien telescope with 50-centimeter primary mirror and 2-lens field corrector. And as well as something interesting that we thought was interesting was the telescope was filled with helium to minimize blurring by internal heat current. So this, we feel it ensures that the data remains clear and without additional noise that's probably unwanted for different observations. And moving on to the integrated sunlight spectrometer, this obtains spectra of the sun integrated over the solar disk and records variations exhibited by spatially unresolved sun as manifested in key diagnostics. And the VSM and the ISS data are actually used together in order to study exoplanet systems and allows scientists to model the influence of the star's magnetic field on the spectrum, which gives us clues to activity levels exoplanets may be subject to. And finally, the full disk control provides full disk images of the sun in a variety of spectral lines. And it takes observations with high temporal cadence in several selected spectral lines as well. And an additional feature is that you can observe Doppler blossom maps using FDP2. And the data collected from the FDP is used mostly for space weather forecasting to help scientists understand triggering and the evolution of solar flares and coronal mass ejections. And just to talk a little bit about the data collected from SOLAS. So the daily full disk line of sunlight photospheric and chromospheric magnetograms, that's something that SOLAS contains. And full disk photospheric magnetograms, and then Doppler maps of the sun as well, like mentioned before, coronal hole maps, and suns as a star spectral observations in several spectral bands spanning low solar atmosphere.
So now I'll talk a bit about GONG. So compared to DKIS, GONG and SOLAS are more like they observe the sun for a long period of time to observe the changes. And so GONG, their hardware is made of Fourier tachometer, and they use helioseismology to use sound waves to measure invisible internal structure and dynamics of a star. So in this case, it's the sun. And it has around 6 locations around the world to make sure that it's always constantly observing the sun no matter where it is. So they have a location in Southern California, Australia, India, Canary Islands, Chile, and Hawaii. And the tachometer has a polarizing Michelson interferometer, narrowband P-filters, and rotating half-wave plate, which is a good measure of the Doppler shift. And the reason why they're studying the sound waves or the waves within the sun is because all the fusion at the core is brought to the surface by convection currents, whose large cells can't be seen at the surface. And these cells tend to change the oscillation periods in a way that lets researchers detect them and measure their properties. And sunspots also inhibit convection, and helioseismology can detect the influence of these sunspots. And GONG data, so some data that, okay, time's up, but I guess to summarize, magnetograms and H-alphas are the data products of GONG data. And using the next slide, this is sort of how they process data. So this is sort of, they use this as a quality assurance, and they do things like FTR that extracts information from the site, and ProCal, which processes the calibration of each image. Vimbical applies acceptance tests to the parameters, and CoPipe computes the camera rotator images for all GONG network sites to align image operation and P modes, merge the images into diagrams, and after it merges, this goes on to the next slide, please. It'll be available on their archive So there are hyperlinks I linked to Solus and Gong data if anyone was interested, and other types of data that you can get access to would be like magnetograms, other image data, helographic maps, and they also have a virtual solar observatory for researchers that want the solar and heliospheric physics data. And that's the end for our slides.
Great. Any questions for Christy and Edward? And note we are at time, so if you have to go, that's okay, but we hope you'll stick around for a question or two.
I had a question for Christy, Laura. Christy, can you put up slide 5 again? That DKIST? I don't know if that's possible. You said there were 5 different pipelines, but the Globus one is really interesting. I was just thinking, what this as again, I'm embarrassing myself because I missed the RCRV presentation, but I'm wondering why the if the academic research fleet should consider I'm just wondering how that might be. This isn't a very good question, but we have this problem with moving data off the ships because of a very narrow bandwidth, and didn't ever really consider anything like Globus for doing that. But do you know what were the other pipelines? Were there 4 other ones?
I'm not sure what the other pipelines are, but I'm just looking at the image on the right, and they have like, it should be 5 data processing the pipelines.
Okay,
And
I think I better understand it now.
yeah,
It just kind of made me think I need to do some homework on Globus, as maybe maybe we can talk offline if you know more about that.
yeah, but I mean, if you're sort of focused on the size of the bandwidth, like for DKIST, like on the slide, it says like they need like 10 gigabyte,
Yeah.
gigabit per second bandwidth. So if that's around the area of what you want.
And are they must be they must be upgrading like the camera stuff and they want to, it sounded like their bandwidth is really poor right now, but they're shooting to increase it. So they must have, then they can use higher megapixel cameras and stuff. Yeah, cool. Very cool. Thank you.
Thank you.
All right, so I don't know if you guys saw, Christine made a comment that DKIST, that is an amazing amount of data per day. I wonder about how much of it will get used and how by end users. Does anybody want to speculate on that one? It'd be a wild guess.
I don't have like an amount, but I will say like through the Gong like data map that I showed, a lot of it, they sort of throw out images that are considered bad or not good enough. And also the actual data archive, a lot of the images are actually like merged into one from every single site at Gong. So I think that reduces the amount of data that is used.
Yeah, thanks. That makes a lot of sense that they kind of do some quality checking and then do some derivation as well.
Way at the end of the pipeline, it gets cooked down into an alert that will fit on a pager message.
All right, any other questions? Oh, here we go. Brian's got one. I'd be curious about the fidelity of the data. Can compressed data reduce the data sizes, but keep scientific validity? Did you read anything about that, you two? That once you compress it or combine it, did they say anything about sort of losing any of the meat of the data? If they didn't, do they compress it?
They do compress it when they send it to Colorado, to a data center. And I'm not sure if it reduces the data sizes, but I know that before they send it, they do some initial processing before.
Yeah, I just want to comment. So that data compression techniques that Frank Capello from Argonne National Lab is working on, that maintain highly compressed data while maintaining the fidelity and scientific accuracy. So if people are interested in that, that's a good place to look at.
Is it lossless compression?
Yes. And it's Frank Capello. I might be misspelling, but I can send you links.
Any others?
Yeah, and I think also I want to point out that the discussion we're having, asking questions between the major facilities, like Chris asking, oh, I see, how did Globus work in the NSO's environment, and is it applicable in hours of a compression? Questions that Brian or Christine, your questions. I think that really shows the value of your students' work, and also the value of CI Compass, bring the different facilities together to look at these things from different points of view. So to the students, Mia, Edward, Ryan, Khushi, and Christy and Nona had to leave. I just want to thank you so much for all your hard work and for really, digging into these major facilities and really bringing us together. So I really appreciate everything that you've done, and I look forward to our continued work together.
Thanks, everyone.
And of course, I want to, since it looks like we're closing out, I want to thank Laura and Angela for running this show so incredibly well, and doing such an awesome job. And Loic, who's been working with the students on the other part of the program, more on the different software engineering practices. So thank you. Laura, Angela.
Thanks everyone for coming. We really appreciate it. And we are recording, so we will make this available if anybody wants it. And maybe we can even put it up on our website if the students don't feel too freaked out about that. And I just want to, because that can be daunting. And I just want to give the students a quick chance to say anything else you guys want to say before we close up. And I know Angela said thank you on chat. Okay, excellent job, y'all.
Thank you so much. It was great seeing everybody. Thank you.
Thanks everyone for coming, and thank you to the students. Fantastic work, everyone.
Great job.
Thanks. Bye.
Bye.
See a lot of student presentations, and this was very, very good.